Now let's look at hypothesis testing about the population proportions. As before, there are three types of hypotheses: one two-tail and two one-tail tests. In all of these, in the null hypothesis, P sub 1 minus P sub 2 equal to 0 is part of the hypothesis, and therefore we can say P sub 1 is equal to P sub 2, and so we combine the two samples for the purpose of generating a common estimate for P and use that in our standard error calculations. So in this respect, this is different from the confidence intervals. In the confidence intervals, we do not pool. We use P sub 1 and P sub 2 individually. Whereas in hypothesis testing, we pool them and use this formula for computing the standard error estimate. Now let's look at an example. So here we're going to use the same example as in the case of confidence interval. Okay. So now we want to test whether the proportion of erroneous tax returns is the same or not, same being the null, not being the alternative. Okay, and the same sample statistics as before. So let's first define the populations and the population proportions. So this will be tax returns filed by Office 1, tax returns by Office 2, and the proportion of erroneous tax returns from Office 1 and Office 2. Okay. Now the sample statistics are exactly like before. Okay. And the point estimate again is calculated like before. That into a percentage, and I'll copy that to the next column. Now the hypothesis we want to test is whether the two offices are same or not. So 0 is the hypothesis value in the right hand side, and we want to test this at 5% level of significance. So point estimate. Now we have the two separate P sub 1s. What we want is a pooled estimate. We want to pool the two together. So we take don't use the P sub 1 and P sub 2. You don't need to. If you did that, then you have to multiply by n and so on. So we have the number of erroneous returns already. So this plus that, okay, divided by the sample sizes. So we are pooling the two together. So that's why it's called a pooled estimate. So this gives us the pooled estimate of erroneous returns for both offices put together. Then the standard error is square root of, so we have P sub 1, P bar, the common pooled estimate, and then 1 minus P bar times 1 minus P bar, and then you multiply by 1 over n sub 1 plus 1 over n sub 2, one right bracket for that, then we need one more for the square root, and that is our standard error of estimate. Then zcalc will be the point estimate for the difference, so which will be P bar sub 1 minus P bar sub 2. Okay, minus 0, so I'll skip that minus 0, otherwise I need one more. Well, I'll do that. I need one more right bracket, so minus 0. So that's the numerator, P bar sub 1 minus P bar sub 2 minus the hypothesized value divided by the standard error of estimate. So that gives us the calculated value of the z statistic, and of course now we can do the test using z-table or the p-value, and we will do both. So here z-table value, because this is a two-tail test, so we need the right hand side tail. So we have norm.s.inv and 1 minus alpha over 2 will give you the z value. So that's the cumulative probability. So you take alpha over 2 to the tail and then do 1 minus that will give you the cumulative probability. So that gives us the calculated z value, and since that gives us the z-table value, since calculated z value is less than z-table value, we cannot reject the null hypothesis. And since this is a two-tail test, we have to really take the absolute value of the z-calc, because z-calc could have been negative also. So you take the absolute value of the calculated z, and if that is greater than the z-table, we reject, otherwise we don't. A p-value approach, so again, for the calculated z, we need to come up with the tail probability. Okay. Now, it is 1 minus, because norm_dist will give you the norm.s dot, you need to go 1 minus norm.s.dist. Okay, now we need to give the absolute value of the z-calc. So make sure that, because it could be both positive or negative, so you need to force it to the positive side, and comma 1 for cumulative probability. So this part will give you the cumulative probability. So when you do 1 minus, you get the tail probability. The number of tails we have is 2, so you multiply the tail value with 2, then you get the p-value. So make that into a percentage. So since p-value is greater than alpha, do not reject. So same conclusion. Then we can provide an interpretation that we do not have sufficient sample evidence to conclude they are different. If we did conclude they are different, and this is the probability of committing type 1 error. So that's the interpretation.